Okay. It is so nice.
Hey everyone, Greg Larson, Executive Director. A year in which we at the Foundation are not only excited
How are we doing a Foundation?
25th anniversary of Young Living.
Say hi.
Now we're going backwards. Let's see it. Okay. Greg's a lot better looking than I am anyway.
There's Susan.
So, it's so nice to be in Chicago in January. It's really funny, I've been traveling a lot. Have you ever awakened in a hotel room and had no idea where you were?
How do I hide these?
I was having a really great dream about marlin fishing in Maui. And I rolled over, looked out the window, and anyway, here we are. Really nice to see all of you. This is a Live Your Passion rally, so I wanted to start by talking about two of my passions. One is our farms. Our farms, how many of you have been to our farms? Our farms are phenomenal, and it really is one of the things that separates Young Living from everyone else in this business. This is a picture actually of the farm in Mona, Utah, growing just a little bit of lavender. My other passion at Young Living is science. And I think most of you know that this past summer I announced the formation of the D. Gary Young Research Institute. And that was primarily to assure all of you that we will continue to carry on in Gary's tradition. Right? We will never sacrifice on the science, on the creativity, on the quality of our products. The other reason that I wanted to have this institute is because I wanted to remind our scientists of the same thing. So every time they come to work and open the door to the laboratories, this symbol is on the door. And they know that they are working in the tradition of Young Living, a great 25-year tradition. So science is really where it's at for me, in addition to the farms. When I can bring those two things together, it's fabulous. And that's one of the things that we do better than anyone else. We really, literally bring science to the farms. In fact, you're going to see a little later this year, we'll be doing a lot more presentations on our farm and the science used in our farms. This happens to be a photo of one of the fellows that works for me. This is Tyler Swift. He is a scientist in the Gary Young Research Institute, but he travels around the world to test our farms. You see, we don't only test our products, we actually test our farms. Now let me show you, this is actually a video, let me just play a second of it. If you look at it very carefully, I think you can see his shirt starting to get wet. He's actually out in the pouring rain. And here he is in Bulgaria testing the soil on the field where we grow Roman chamomile. That's dedication. He's out there in the rainstorm. He actually did come home sick and he called in sick for one day. I let him have it off. But this is what we do all around the world. We test our water, our soil, our seeds, our plants, our oils, our finished products. We test and we test and we test and we test. And in fact, every bottle of oil that you receive has probably, don't quote me on this because everyone's a little bit different, but it's been tested about 90. It's 90 times before it gets into your hands with different types of tests. I don't know of any place that does that better. Frankly, there isn't a place that does that better. I'm really proud of it. I have a question for all of you. Does Young Living make pure essential oils? Who said no? You've heard this before, but you're absolutely right. You are absolutely right. Only plants can make pure essential oils. If any company tells you they make oils, watch out. Don't trust them. Because that means they're doing it in a lab. Now, the way plants make oils is absolutely fascinating to me. I wanted to share just a little bit of it with you. Plants actually have cellular structures on their exteriors that are called glandular trichomes. They're actually kind of the equivalent to a gland on our bodies. They secrete things, and these glandular trichomes secrete essential oils. And this is actually why I went to school for chemistry, because I can't draw. This is about as good as I can get at rendering something artistically. But this is what a glandular trichome looks like, at least schematically. There's a basal cell, just like we have basal cells on our skin, that supports this little structure that appears on the exterior of the cell, of the plant. And the working part of this trichome is what's labeled there as the secretory cells. They actually produce the essential oils, and they secrete them. But what's really, really cool is that they secrete them into little bags, and that's kind of what I've drawn there. It's called the subcuticular oil storage cavity, or little bag. Now, there happens to be a couple who live in Russia. This was actually, they started in the Soviet Union, they're still in Russia today, named the Svobodas. And they've devoted their lives to studying plants under the microscope. And they've got some fantastic photos of these subcuticular glands. Let me show you what some of them look like. If you zoom in on a peppermint leaf about 1,000 times, this is what you would see. And here are the little oil storage bags on the exterior of the leaf. This is what it looks like on a hazel leaf. Very similar in structure. And of course, these particular photos show the bags filled with oil. They're kind of inflated already. They start out as a flat structure, and then they kind of pop up almost like Jiffy Pop popcorn as the oils come out. This is a shot of Roman chamomile. And the reason I like this particular photo is that the one on this side has lighting behind it so you can see how transparent it is. These are incredibly delicate little structures. And what you're looking at here is actually what we call a Roman chamomile floret. It's a piece of the flower. The flowers are made up kind of smaller flowers that we call florets. So this is actually on the surface of the Roman chamomile flower. Now, these things vary a little bit through nature, and on citrus fruits, they're still on the exterior of the fruit, but they don't form those little subcuticular oil storage cavities. Instead, they're just under the exterior of the fruit. They're in the rind. And of course, that's why chefs like to take things like orange and lemon zest, because that's where all of these natural essential oils are. Even on seeds, there are oil storage cavities. On seeds, they're called vitae. And this is actually a photo of a caraway seed that's been cut in half, broken open. And what you can see here is little vitae, they're kind of pockets around the exterior of the seed that hold the oils. And that's actually why if you take almost any raw seed and you rub it between your fingers, you'll see oil on your fingers, because it's on the exterior, and you'll rub it right off. You break those little vitae open and rub the oil onto your hand. Now, how many of you have been to our farms again? Let me see. So a number of you have seen the distillation process. This is really, really cool in kind of two ways. The first is that it is the modern way we do it. The second is that there are records dating back to 5000 BC of people doing it almost the same way. They didn't have stainless steel, obviously, but they were using it in clay pots, and they were doing it the same way. This is the way we extract the oil out of those small glands on the plants and get it into your hands. So let me show you what this is. This is a photo of the Mona farm, and the actual still itself, or what we call the cooking pot, is right there with that arrow. Each one of these stills is quite large. They're 18,000 liters. So that goes down into the ground about 10 feet from where you can see it here on the surface. It's a big buried sort of pot. And we have, at the moment, 13 of these at Mona, and they're running most of the time. Now, what happens is you put the plant material into the part that I have the arrow pointed to, and then you close the lid. And then you turn on the steam. The steam rises up from the bottom, and it carries the oils with it, and it rises up to the top, up through the plant material, into this area. And then it comes down the pipe and into this device, which is called a condenser. Now the condenser has cold water flowing around the outside of it. It doesn't mix with the oil, it just flows around through the system in pipes. And that's to cool it off, because we don't want to expose oils to heat for very long. So what we do is we drive them off the plants, the steam carries over and it's immediately chilled. So when it's chilled, it becomes a liquid and it flows down because of gravity. And you can see that that condenser actually is going through a metal grate. It goes down into a room that's below this picture. And this is what the room looks like. So right here is the bottom of that condenser.
We've been there.
Okay? So at this point, the liquid, water, and oil mixture is flowing to the bottom, and then it comes down through this pipe and into this device, which is the separator. Okay. This is where all the flow kind of stops. The liquids stop moving and they're allowed to separate because I think most of you know oil floats on water. So if you stop the flow, the oil will float to the top. And then it comes up into this glass collection device. If you look closely, there's one you can see. This is juniper oil floating on top of the water in the collector. Okay? Now, what you're looking at there is about 1.5 liters, maybe 2 liters of oil. Okay? For something like lavender, what's required to produce that amount of oil is anywhere from 1/4 to 1/2 acre of lavender plants. This is an incredibly concentrated ingredient, these essential oils. And if you just think about how much oil Young Living sells in a year, think of the acreage of plants that we need to produce that kind of oil. One of the reasons I'm telling you this is because this is one of the main reasons that essential oils are so expensive, right? You just can't do it any other way. You need a lot of plants and a lot of acreage and a lot of labor to harvest the plants and distill it and produce these oils, and it becomes very expensive. If you ever see an oil that's relatively cheap, it's the $5 stuff at Walmart, you know it's not real. It can't possibly be real. It's synthetic because it just cannot be produced inexpensively.
I can't.
I was watching a television show this morning in my hotel room. I don't know who he was, some self-proclaimed health expert, chef, and he was cooking. Did you see it this morning? And he said, just throw a little oil in here. He was making his own bath bombs. Just throw a little oil in here. I get it at Walmart. It's about $5. Anyway, this is how we make the real stuff, the good stuff, the best stuff, the only stuff. Okay?
Yeah. Now,
did you ever wonder what really happens when you diffuse oil and you inhale it? Yeah. Oh, good. At least there's one other nerve. This is the kind of stuff I think about a lot. So let me walk you through the physiology of what happens. This is a cross-section of a face. Probably my face, but it has a pretty big nose. Okay? If you could look inside the sinus cavity, you would be able to see, and I apologize, it's a little tough to see on this screen. Let me go back and forth. You would be able to see these little hair-like structures that come down into the sinus cavity from the top. Those are olfactory nerves. That's the scientist's big word for smell nerves. Okay? Olfaction is your sense of smell. They actually protrude down into the sinus cavity like little fingers. I kind of got tired of drawing them on here, but in the real human body, you would have over 1 million of those olfactory nerves in your sinus cavity. Now, you take a breath, and what happens? Little molecules of whatever you're smelling within your sinus cavity. Okay, so those, pick your favorite essential oil. Those are the molecules from the essential oil. And within microseconds, milliseconds, those molecules move around and attach themselves to your olfactory nerves. Okay? Starting to stimulate the nerves. This is the beginning of your ability to actually smell something. Now, if I had a magic microscope and I could look at one of those nerves, it would look like this. A little bit like it. I always get hungry for sushi at this point. It looks like a Anyway, this is what a typical nerve cell looks like. Over on the left side are what we call the dendrites, and over on the right side, the sort of tail of the squid, is the axon. And what happens is that those little dendrites are the things that I showed you in the first diagram. That's actually what sticks down into the nasal cavity. And that's where the molecules of whatever fragrance it is bind. Okay? Now, if you could sort of zoom in on any part of the cell here and look at its membrane, like this, and zoom in again, this is what you would see. These are called receptors. In this case, they're olfactory receptors, smell receptors. Receptors are those things that look kind of like pears. They are huge protein molecules that are so big they actually go across the cellular membrane. So they stick out on the outside of the cell, and they go through right to the inside of the cell. These receptors are really, really important. I love receptors. They do so much in your body. They have very specific binding sites on them, and that's what's represented by the little dark ovals on the top of each receptor. I should point out that in this particular diagram, the top of the diagram would be outside the cell, the bottom of the diagram is inside the cell, and that cellular membrane goes the whole way around the cell, okay? So you have these little pear-like proteins that we call receptors. And there's a couple of things to remember about them. They have these binding sites, which I'll get to in a minute. The other thing that's important to know about receptors is that they control the flow of ions, which are nothing more than charged molecules across the membrane. So every cell constantly works to pump positive ions out of itself. So things like sodium and calcium and potassium, they all have a positive charge. And cells actually burn up a lot of energy constantly pumping those charged molecules out of those cells to put them on the exterior of the cell. So what happens is you actually end up with kind of a positive charge because they're charged molecules on the outside of the cell. It's almost like a static charge. Positive outside, negative inside. Now here's where the receptors come in. When a particular fragrance molecule comes floating along, it can bind at one of those receptor binding sites. Now, this is a very, very specific thing. It's almost like a lock fitting in, or a key fitting into a lock. Those receptor binding sites all have a special shape, a special size, and a special, what we call distribution of charge, the way charged things can line up into them. And only certain molecules can fit into those binding sites. They're very, very specific. Luckily for us, we know of at least 400 different types of smell receptors, and there are probably 10,000 of those on each nerve cell, and we have over 1 million nerve cells. And that gives us lots and lots of combinations to use, and that allows human beings to, believe it or not, recognize over 1 trillion different fragrances. A lot. We really don't even know what our brain processes all the time, recognizing the fragrances. But let me get back to the physiology a little bit. As I was saying before, the cell pushes all the positive ions to the outside. When a fragrance comes along and binds at one of these little binding sites, it changes the shape of the receptor molecule, and that allows a channel to open in the receptor molecule, and all those positive ions come rushing back to the inside. That means that you've got charge actually moving across the membrane of the cell. I'm sorry, I know this is kind of confusing. This is pretty deep. But this is critical. And this is absolutely astounding to me. Whoever engineered this was pretty smart. Because what this does is change a chemical into an electrical signal. Because when those charged molecules rush across the membrane, it makes an electrical charge. You're moving charge, and that by definition is electricity. So let me show you, I have an animation of this. Let me show you what it looks like. So here are the receptors sticking up outside of a cell, and along comes some fragrance molecules. If that one didn't fit into the binding site, along comes one that does fit. A channel opens. Now ions can rush through that channel, and all of a sudden there's an electrical charge that goes down the outside of the membrane.
That's
really cool.
That is cool.
These are nerve cells, so you know what that electrical charge is. It's a nerve impulse. Right? It's what people talk about all the time, oh, my nerves aren't firing, my nerves are firing. That's your nerve impulse, right? So that is the way neurons change chemistry into electricity, right? Now, once that happens, the electrical signal takes off, it goes up a chain of nerves, and it goes to the brain or wherever else it has to go. Usually to the brain. In the case of olfactory nerves, the ones in your nose, it goes directly to the brain.
The limbic
That's a
bulb.
brain. And it actually goes to a particular part of the brain, which I'll get to in a moment. This, I've greatly oversimplified, as you can imagine. But this was absolutely groundbreaking work when it was discovered. And in fact, here are two friends of mine, actually, Richard Axel and Linda Buch. These are the two people who discovered this mechanism of transferring chemistry into electrical signals and getting it to the brain. And this is them receiving the Nobel Prize in 2004. So this was a big deal. This was one of the biggest discoveries in science in the 20th century. And now we kind of take it for granted. And all of you look like you're really taking it for granted. Is anybody still awake? Back to the brain. After Richard and Linda discovered that mechanism, there was a lot of work done. As you can imagine, when someone wins a Nobel Prize, other scientists think that's pretty interesting and they start to look at it. And what we now know since that work is that the signal not only goes to the brain, but it goes to a very specific part of the brain. Part that most of you probably heard of, the limbic system, which is the colored region in this diagram. Not only that, but it goes to a specific part of the limbic system called the amygdala, which is kind of the little circular thing right at the bottom, right there in the middle. Again, for us to know this is a big deal, and it involved a lot of science. Let me tell you where that came from. This is a good friend of mine, Pam Dalton. Pam works at at a research institute called the Monell Institute. It's located in Philadelphia, on the campus of the University of Pennsylvania. It's a pretty nondescript building, actually. This is the Monell Institute. It's right on Market Street. It looks just almost like a factory. Except there's one distinguishing feature. When you get to the door, there's a big nose and a mouth. That's because the Monell Institute is the world's premier facility for studying both smell and taste, those two senses. It's all they focus on. There are about 150 PhD scientists that work at the Monell Institute, and you have to be invited to work there. So people apply from all around the world to work at Monell. And so this is kind of the place for sensory scientists to go and learn about the senses. Now, Pam's one of the principal investigators there, and she did some fascinating, you know what, I should tell you this too, a little story about the Monell Institute. The Monell Institute is sponsored by government grants, but it's also sponsored by industry, by different companies. And the companies actually have to be vetted and invited to join the Monell Institute. So when I joined Young Living, I went to the Monell Institute and I said, we'd like to be a sponsor, we'd like to join you, we'd like to help with your research. And of course that gives us access to all of the hundreds of scientists to learn about the senses. And you know, I had some contacts there from past life, and I was talking to them and they said, oh, that's really interesting. There was another company that came to Manila a few months ago. I think they were called Dudera or something. And she said, what do you think of them? So I told them. And now we're members and doTERRA isn't. So anyway, on the story.
My phone is
Campbell did some amazing work. She did functional MRI, magnetic resonance imaging. And what that is really a way to measure the activity of brain cells. It measures the oxygen flow through the blood of certain parts of the brain. And when you take an image of a brain like this, there are parts of it that light up. Those are the parts that are working hard at the moment. This is what she did. And this is just one example. She did this on hundreds of people. This happens to be a female who volunteered for this study. And this female was inhaling rose oil, rose essential oil. And you can see that the part of her brain lit up, and it's the amygdala. Okay? Now, this same woman came back a few days later, and they put her in a dark room and put her in the scanner again. And this time, they played the voice of her daughter, saying, "I love you, Mom." And this is what lit up. It's the same part of the brain. It's that amygdala. Okay? What that kind of work proves is that our oils are going to the same part of the brain that controls our emotions. Okay? So when we talk about oils being uplifting, or calming, or soothing, or anything emotional, it's hardwired that way. This is real science. Okay? It's not what you think it would smell like. It's very this strong. Is real science. It actually does.
Like it's not like, oh, that's lovely, right off the bottle.
So I think that's absolutely fascinating work.
Yeah, it's not. But when you
remember
do,
this, I
like,
showed you this before. That you're putting your nerve signals off to your brain or wherever they're going.
Then it's like, oh,
as with everything in science,
you know.
it's not quite that simple. And here's why. Those nerves line up like this. This is now a nerve fiber. It's a bunch of nerve cells in a row.
One drop.
But what you'll notice is that those little squids don't really touch. Right? So how in the world does a nerve signal go the whole way down a fiber when it's not connected? This is like trying to put an electrical signal through a wire that's cut into pieces. Right? So there are these spots called synapses. You've all heard of synapses. They're the gaps between the nerves. This is where it gets really, really interesting. The nerve signal comes down the nerve fiber until it gets to the synapse. And this is an electrical signal, remember, it's like a spark almost moving down the nerve. When it gets to the synapse, it has to stop. It can't jump across the gap. But the nerve is designed so that that potential change, that charge coming down the nerve, when it gets to the end, triggers the release of chemicals. So now you take an electrical signal. You started with a chemical signal, it became electricity. Now you're taking the electricity back to chemical. This happens back and forth through a nerve change. So it releases chemicals. Those chemicals drift across the synapse to the next nerve, where they bind at receptors, and those receptors cause a new electrical spike in the next nerve, and so on and so forth. This moves almost at the speed of light. It's incredibly fast. But those synapses, because they're gaps, require chemicals to carry the message across them. If you could see it, it would look something like this. Now, those chemical molecules drifting across that gap from nerve to nerve carry the nerve's signal. Right? They carry the nerve's code. That's why those chemicals are called neurotransmitters. I think you've all heard of that. They transmit the signal from nerve to nerve to nerve. Okay? These neurotransmitters are the key to almost all of our functions. There are some scientists who believe that neurotransmitters are close to the definition of life, okay, because they code all the information in our nervous system. Now, yeah, I thought this might be a little bit the reason I told you all of that is because one of the most important parts of the neurotransmitter system in human beings is something called the endocannabinoid system. Endocannabinoids, I should say cannabinoids, are neurotransmitters. The endocannabinoid system is a system of neurotransmitters and their respective binding sites, which are the receptors, and then how the whole thing comes together. So that's the endocannabinoid system. It's an extremely complicated system. Scientists are still studying it. It's not really all that well known yet. But one of the things we do know is that there are at least two distinct types of receptors in the endocannabinoid system. These are two of the receptors that the neurotransmitters go between when you jump signals from nerve to nerve to nerve. And they're cleverly named cannabinoid 1 and cannabinoid 2. CD1, CD2. Those are the two receptors we know about. There are quite a few scientists around the world who suspect that there may be a dozen or more different types of receptors, but these are the only two that have been positively identified so far. So stay tuned. This story is going to get more and more interesting. You ready? Yes. Okay. Back to the story. I just want to re-emphasize, okay? All of these receptors you're saying are very similar. Endocannabinoid receptors are the same, basically, as your smell receptors in your nose, except these exist between all of your nerves, all over your body. But it's the same thing. The difference is that these receptors have binding sites that are tuned to pick up different molecules. These don't pick up fragrance molecules. They pick up molecules in your body that are designed to transmit signals between nerves. One of those molecules is called anandamide. Anandamide is a compound that you make all the time in your body, and it's used as a neurotransmitter to allow signals to go to your brain and to your muscles and to all other parts of your body that have nerves. Okay? Here's where it gets a little interesting. Oh, sorry, there's my lock and key thing again. You remember that already, right? Yeah. This is very specific binding. These receptors are tuned to pick up anandamide. But here's where it gets interesting. Plants make compounds with structures that are so similar to anandamide that they fit in the same receptors. Okay? So the lock isn't quite as specific for the particular key. Okay? Two of those compounds happen to be THC and CBD. You ever heard of those?
Maybe.
Okay. Now it happens that and there's always a few exceptions here, but it happens that primarily THC binds at CB1 receptors, and CBD, or cannabinol, binds at CB2 receptors. So they bind at different receptors, which means they signal things differently in your nervous system. And I think you know, THC, tetrahydrocannabinol, signals some pretty interesting things in your brain. This is the plant responsible for it, right? This is a marigold. No, sorry. When I lived in Hawaii, this was known as Maui Wowie.
Maui
Or called Lolo. So this is Maui Wowie, right? And it is very, very THC is very, very concentrated in this plant. Okay? There's a whole lot more THC in marijuana than there is CBD, okay? Although both compounds exist. Marijuana can be anywhere from 15 to 40% THC and very little CBD. Now there's another plant that's in the same family. Here it is. This is hemp. This is the opposite. Hemp is very heavy in CBD, but very light in THC. Hemp very rarely has more than 0.3% THC in it. Okay? And in fact, at that level, you won't see or feel any of the sort of expected effects that you would get from Maui Wowie from hemp. So you won't get any of those cognitive dissociations, you won't get any hallucinogenic effects or anything like that, because CBD doesn't trigger it, only THC does. Okay? So as I said, if you distill either one of these plants, you will get a mixture of THC and CBD. The difference is in the ratio. And of course, for our purposes, we would like everyone to have the endocannabinoid system benefits without the hallucinogenic without the hallucinogenic effects of the THC.
I mean.
So we choose not to use marijuana and having THC. People who use that tend to look a little more like this. People who recommend the use of CBD, on the other hand, look a little more like this. Now, CBD binds almost everywhere in the endocannabinoid system, and the endocannabinoid system is vast. Okay? The endocannabinoid system has influence on all of the systems listed here. Okay. This is still in its infancy. Okay. There were a lot of people who studied the effects of THC on the endocannabinoid system in the 70s and 80s, but they can't remember anything. So the science is kind of starting over again, the CBD. Okay? And we're trying to understand exactly what it does affect. What we do know is because the endocannabinoid system is so vast, it seems to have different effects on different people. And I am not going to stand here right now and tell you how to talk about this compliantly. We will. Okay, when we get to the point where we launch CBD oil, which we will do, we will talk to you about what we can say about it. For now, what you have to understand is it does affect everyone a little differently, so you're going to hear all sorts of different stories. And frankly, that's why everyone today is singing the praises of CBD. Because it affects everyone and it affects everyone. Okay? Now, that's where I'm going to end my presentation today. What I thought I would do though, since we're all together, I don't get a chance to be in a room with 300 friends that often, I would open it up to some questions and we can have a little bit of a discussion if you like.
I want to remind everybody that now is when you stop your recordings. We are not recording the question and answer time. So we ask for the honor of that. You got to record all of that and not recording question and answer, okay? Because we cannot control.
Hi guys.
Is that
We
mic
can't
not working?
record this part.